By now, whenever I say that there is model parameters and we are increasing the number of model parameters, I'm assuming that you are thinking one thing. What is that? I am thinking overfitting, which means that your training performance or the model will emit really low error during training, but when you are exposing that model to the outside world for new unforeseen data on which it will run, you will get errors much larger. So whenever you add more parameters to the model, you have to guard against that. Now there are several ways of doing it, and in neural networks, dropout is one of them. So let's see what dropout means. Before we get into that, the problem we are trying to address here is overfitting. What it means is the model works great with training data. With new data, however, which is unseen during training, results in high prediction error. So the classical approach, which I assume some of you or most of you should be familiar with as a part of your ML basics, is the regularization, which is L1 and L2 regularization. Some other techniques that are also taught in many machine learning courses are data augmentation or train with noise added. Early stopping is another technique that is often used in machine learning. If you are not familiar with these techniques, I'll recommend that you go back to your machine learning course to get a refresher on these topics. In this one, we will talk about dropout, which is extremely effective to tackle overfitting in neural networks. You are familiar with multi-layer perceptron. Let's work out what multi-layer perceptrons would be in the context of dropouts. So dropouts means simply ignoring the activations from certain number of randomly chosen nodes during training time. It was a neat little innovation from the Toronto group, which is captured in this paper. You can look it up. It's a fairly simple technique, but very powerful. You choose with certain probability that you're going to knock off a random set of outputs or the activations from the nodes, which means that during training phase you're not going to update the weights and the biases associated with these nodes. In one iteration, you may knock off the nodes shown here, and in another instance you may choose a different set of nodes. So what does this mean in terms of how the activations are being calculated? Let's work that out. Let's say we have the probability P with which we are going to drop these nodes, and this probability can be anywhere between 0 and 1. We do not want to choose 0, or 1 would be the degenerate case where we don't drop anything. So we don't want to drop all the nodes, and you don't want to keep all of them because that would be equivalent to not having dropouts. So now say we drop half of these nodes. So that means probability would be 0.5. If say I take this node and I am going to not update it with a probability of P to this node, those weights aren't going to get updated for that particular iteration when it is not chosen. So in this case, this iteration it is chosen, but in this iteration this one is not chosen. In other words, the output that would come out of this node would be scaled back by the probability that you pass in as a parameter. So the output would be chosen p times the output, and 1 minus p times the times that are not chosen, the output would be 0. So effectively what you will have, the nodes emit is p times output tube. Now all the nodes are going to be randomly dropped, and correspondingly the output will be scaled down by a factor of p. So what do we do with a network where you have these fully connected nodes and this one where the output is scaled out by p? One thought might be, at runtime you are going to run inputs through all the nodes, and at each node you can scale it up by a factor of p. Now remember that at test time or at predict time, if you have to multiply each output of a node with a factor of p, that would eat into your computation time. And if you are running it on a device, any device, it would eat up some cycles of that device to do this scale up. So what popularly people do is, instead of scaling the output at test time, you can do something called an inverted dropout. And what it means, it performs the scaling of the neurons at training time itself and are pre-scaled. So these nodes at training time itself will get pre-scaled so that at runtime you don't have to do any of this scaling. So it's a neat little trick, very important one. You don't have to worry about this because the toolkits that are available and the ones that are going to use for this course already take care of it, but it's important for you to understand what the dropout node does.